Welcome to the video lecture on Parametric Equations and Calculus. We say that a curve C represented by the parametric equations x equals f of t and y equals to g of t on an interval I is called smooth if f prime of t and g prime of t are continuous and not simultaneously zero except possibly at the endpoints of our interval I. We say that a curve C is piecewise smooth if it is smooth on each subinterval of some partition of this interval I. So let's consider the parametric curve x equals t minus sine of t and y equals 1 minus cosine of t. The graph of that looks like this graph right here. And what we want to do is find the places where this curve C is not smooth. This is called a cycloid. So what we're going to look at are the derivatives first, and we want to make sure that our derivatives are continuous and they are not simultaneously zero. So that's what we're going to look at. So if we start with our x function, x is equal to t minus sine of t, and y is equal to 1 minus cosine of t. So that means x prime would be the derivative, which is 1, and then the derivative of a minus sine of t, the minus stays there, and derivative of sine of t becomes cosine of t. And that's a continuous function because cosine is continuous, so 1 minus cosine of t would be continuous as well. If we look at y prime, the derivative of y is just going to be the derivative of negative cosine t, and the derivative of negative cosine t is positive sine of t. So that's also a continuous function. So both of our derivatives are continuous. The other thing that we need to check is, are they simultaneously zero? So we want to see, when are these two different derivatives going to possibly equal to zero? So if we set x prime equal to 0 and solve this, we're going to need to subtract that cosine of t. It is being subtracted already, so let's add it to the left-hand side. And where does cosine of t equal to 1? Well, that's going to be at angles that are equal to 0 or 2 pi or any multiple of 2 pi. So we could write this more generally as 2 pi k. Any multiple of 2 pi k, where k here is an integer starting at 0, 1, 2, 3, or negative 1, negative 2, negative 3, and so forth. So now let's look at where the y prime derivative might possibly be 0. So when does sine of t equal to 0? Well, that's also going to happen at 0, at pi as well, and at 2 pi, and so forth. So this time we're talking about all multiples of pi. So this would be pi k for our values of t. So what we want to make sure of, if we're going to be considered smooth, is that we don't want our t's to be simultaneously, we don't want these derivatives to be simultaneously zero. So we're looking for t's where these would overlap. So in this case, we don't want the pi and the 3 pi and the 5 pi, but we do want to look at the 0 and the 2 pi and the 4 pi, etc. So the 2 pi k represents a way of generalizing all those even multiples of pi which would overlap, which are both solutions to these derivatives being equal to 0. So they are simultaneously going to equal to 0, these derivatives, at t equal to 2 pi k, those even multiples of pi. So if we look at what the x values are that correspond to those and the y values are that correspond to those, then if we go back to our equation for x and we plug in 2 pi k into that, then this t would get replaced with 2 pi k minus sine of 2 pi k. And sine of 2 pi k is sine of 0, sine of 2 pi, sine of 4 pi, sine of 6 pi, etc. Those are always 0. So this goes to 0. So that means the x coordinates are going to look like multiples of 2 pi. Now let's find out what the y coordinates are that correspond to these particular t values. So if we go up here to our function for y and substitute in 2 pi k in for that t, we'll get 1 minus cosine of 2 pi k, and cosine of 0 is 1, cosine of 2 pi is 1, cosine of 4 pi is 1. So this cosine of 2 pi k is always equal to 1. Therefore, we're always going to get 1 minus 1, which is 0. So that means this graph up here, this cycloid, is going to be smooth everywhere except at these points where the derivatives were simultaneously equal to 0. So this is smooth everywhere except the points that have the form 2 pi k for the x value and 0 for the y value. So if you look at this graph up here, this would be 0, this is 2 pi, this is 4 pi. And so these points right here correspond to these cusps in the graph. And these would not be considered smooth points. Okay? Now, if you recall from our previous lecture on parametric equations, we talked about the equations of motion used to represent parametrically the path of a projectile fired from the ground. So we're going to use these equations to parametrically represent the path of a projectile fired from the ground at an angle of 45 degrees with an initial velocity of 48 feet per second. So just to remind you, the equations of motion were x equals v sub 0 cosine theta t, so that gives you that horizontal motion, and then y equals the initial height h plus that initial velocity v sub 0 sine of theta t minus 16t squared, and that gives you that vertical height. So in our problem, if we're doing 45 degrees, cosine of 45 degrees and sine of 45 degrees is root 2 over 2, and our initial velocity v sub 0 is 48, and our height from the ground initially is 0. So our h is 0, our v sub 0 is 48, so 48 times root 2 over 2 is going to be 24 root 2. So simplified, this would be 24 root 2t is equal to our x, and y is equal to 24 root 2t minus 16t squared. So we know that the object was projected initially at 45 degrees, but how could we find the angle at some other time? You know, as you move up, these angles are going to get smaller and smaller until eventually when you reach that maximum, there's no angle at all because this tangent line right here would be zero slope. So then when we come back down again, then these angles are now going to be going in the other direction and getting steeper and steeper as I go down. So we're trying to figure out how we could find the angle at any other time and how we could find that maximum height. So the following theorem is going to help us do that. It's the theorem that helps us determine the derivative, which is going to be the slope of those tangent lines, which also corresponds to that angle of inclination or angle of depression going down. So here's what the theorem says. If you have a smooth curve C given by the equations x equals f of t and y equals to g of t, then the slope of the curve at a point x comma y is given by dy dx, and we can calculate that derivative through the parametric equations by taking dy dt over dx dt. And here we need to assume that dx dt is not 0, otherwise we would be dividing by 0. So parametrically, to find the derivative, you take the derivative of the y function with respect to t divided by the derivative of the x function with respect to t. So let's find the derivative of the parametric equations x equals t cubed plus 1 and y equals t minus 1. So our definition is that dy dx is going to be dy dt over dx dt. So in this problem, if our y is equal to t minus 1, then that means dy dt is just the derivative of t, which is 1. So this numerator is a 1. And if x is t cubed plus 1, then that means dx dt is going to be 3t squared. So our denominator will be 3t squared, so the overall derivative is 1 over 3t squared. Now you can leave it in terms of t if you like, if you want to get fancy, especially since we're writing this notation as dy over dx. Sometimes it's nice to have this equation either in terms of the variable y or in terms of the variable x instead of in terms of t. So if you wanted to turn this in terms of the variable y, you could go over to the fact that we have y equals t minus 1, so that means y plus 1 is equal to t. So in terms of y, this would be the same as 1 over 3 times, and then I'm going to replace this t with y plus 1, quantity squared. So the derivative would also be equal to that. Now if you wanted to know what this was in terms of x, then you could go over here and solve this for t. So we could subtract 1, and then we could take a cube root. And so this would become 1 over 3 times t, which is this cube root of x minus 1. I'm going to write that cube root as a 1/3 power, and we also want to square this t, so I'm going to put the square on the top. So you could also write your derivative this way in terms of x's. Now let's see if we can answer our question that we were asking earlier. Find the derivative of x equals 48 square root of 2 over 2t, y equals 0 plus 24 root 2t minus 16t squared. So there's our x and y parametric equations for the equations of motion when we have this projectile fired from the ground at an angle of 45 degrees with an initial velocity of 48 feet per second. And we're going to use it to find the angle of elevation when t is equal to 1. So we have this motion like this, and after 1 second, which might be sometime over here, what is this angle of inclination? And you can imagine that's going to be just like this little tangent line right here. And if you drop down a perpendicular and make a little right triangle out of this, it's this angle that we're talking about. And that angle is like your rise over your run, which we also know as slope. So the tangent of that angle would be the opposite over the adjacent. So tangent of that theta would be our rise over our run, otherwise known as our slope. So if we can calculate our slope, also known as the derivative, then we'll be able to figure out the tangent of theta, and then we can undo the tangent to find out what this angle of theta happens to be. So this slope is going to be our derivative, so let's work on finding that derivative first, and then we're going to set that equal to tangent of theta to help us find this angle of inclination. So what would dy dx be for this particular problem? Remember, it's going to be dy over dt divided by dx over dt. So here's my parametric equations. Dy dt is going to be the derivative of this equation right here. So the 0 goes away. The derivative of 24 root 2t is going to be 24 root 2. And the derivative of minus 16t squared is minus 32t. So there's our derivative of y. Now let's do our derivative of x. Remember that this reduces to 24 root 2t, so the derivative of that would just be 24 root 2. Now, when do we want this derivative at? What point in time? We want this derivative at t equals to 1. So now let's plug in 1 for t. So our slope at t equals to 1 is going to equal 24 root 2 minus 32 times 1, which is just 32, over 24 root 2. And what we said over here is that this slope at time 1 is equivalent to the tangent of our angle of inclination, what I'm calling theta. So if we set this expression equal to the tangent of theta, then we can solve this for theta by taking the inverse tangent of this expression. And then you would just type this into your calculator. You would do inverse tangent of parentheses 24 root 2 minus 32, use parentheses around your numerator, and then divide that by 24 root 2. Now, depending on what mode you're in, you could either do this in radians or you could do this in degrees. So if you do this on your calculator, here are the two different values that you'll get. You'll either get 0.057 radians if you're in radian mode, or 3.27 degrees if you're in degree mode. So the angle of inclination is about a little over 3 degrees, or 0.057 radians. Now, because dy dx is a function of t, usually, we can use the previous theorem repeatedly to find higher order derivatives. So for example, if you wanted the second derivative, then you would take the derivative with respect to x of this dy dx formula. So to do that, you would take the derivative with respect to t of dy dx and then divide that by the derivative of x with respect to t. So notice that we're not just taking the derivative of our first derivative, or taking the derivative with respect to t of our first derivative, and then we have to divide that again by another dx dt. Similarly, for the third derivative, we would take the second derivative's derivative, so we would take the derivative with respect to t of our second derivative and divide again by dx dt. So every time you're taking a derivative, you have to divide again by that dx dt. So for example, if we want to find the first, second, and third derivative of these parametric equations, we would start by finding dy dx, which is dy dt over dx dt. So dy dt is going to just be the derivative of 5t cubed minus 3, which is just 15t squared. Then we divide that by the derivative of x with respect to t, which is just going to be a 2t. And if we reduce this, this just becomes 15 halves, and then we get a single t since the t squared over t reduces. So there's our first derivative, y prime. So to find the second derivative, d squared y dx squared, here's what we have to do. We have to take the derivative with respect to t of this answer that we just got, but then we have to divide that again by another dx dt. So the derivative of our answer, the derivative of this y prime, would just be 15 halves, and then we have to divide that by another dx dt, and remember that dx dt was 2t. So when we simplify this, this is just going to be the same as 15 over 4t, and there's our second derivative. If you want, you could think of that as 15 fourths and then a t to the negative 1. And you're probably going to want to think of it that way when we go to find our third derivative, because our third derivative is going to be the derivative with respect to t of this answer, so this second derivative that we just got, divided by another dx dt. So the derivative of this answer, when I bring down my negative 1, I'm going to get a negative 15 fourths t to the negative 2, and then I have to divide by dx dt again, which is another 2t. So this is going to become a negative 15. The 4 and the 2 join together to form an 8. The t squared joins the t on the bottom, giving me a t cubed. So my third derivative is negative 15 over 8t cubed. So let's find, using those same parametric equations, let's find the equation of the tangent line when t is 1. So there's a couple things you need to know to find the equation of a tangent line. You need to know your slope m, and then you need to know a point that you're going to go through, your x comma y. So remember from up here that we knew that y prime was 15 halves times t, and we had parametric equations x equals t squared and y equals 5t cubed minus 3. So how do I find the slope m when t is 1? Well, here's the derivative at any t. So if I plug in 1 into that, that tells me that the slope that I want to use is 15 halves. How do I find the x and the y that corresponds to t equaling 1? Well, I just plug in 1 for these t's. If I plug in 1 into t squared, I'm just going to get 1 back again. So the x coordinate is 1. If I plug 1 into y's formula, I'm going to get 5 minus 3, which is 2. So the point that I want to go through is 1 comma 2. So now that I know a point and a slope, I'm going to use point-slope form. So this is going to be y minus 2 equals our slope, 15 halves, times x minus 1. So we get y minus 2 equals 15 halves x minus 15 halves. And when I add 2 to both sides, that tells me that my tangent line is going to be y equals 15 halves x minus 2 is the same as 4 halves. So negative 15 halves plus 4 halves is negative 11 halves. And there's my tangent line. Now to find vertical and horizontal tangent lines, remember that our derivative dy dx is really dy dt over dx dt. So to find a horizontal tangent line, that's going to be when your slope is 0, when your derivative is 0. And this fraction will only be 0 if your numerator is 0. So to find a horizontal tangent line, we're going to find when dy dt equals to 0. And we want to make sure that that happens assuming that the denominator is not also 0, because then we won't necessarily get a 0 slope. We would get one of those indeterminate forms. Likewise, to find a vertical tangent line, that's going to be when our dy dx is undefined. And for a fraction becomes undefined when its denominator is 0. So we're going to find our vertical tangent lines by setting this denominator, which is dx dt, equal to 0. And again, we want to assume there that the top is not also 0 at the same time. If both the dy dt and the dx dt are both 0 at the same time, then no conclusion can be drawn without further investigating. So, for example, suppose that I want to find all the points of vertical and horizontal tangency to the curve x equals cosine t and y equals 2 sine 2t. So, to determine the vertical tangent lines, you set dx dt equal to 0. So let's find out what dx dt would be. If x is cosine t, then dx dt is going to be minus sine t, and we want to know when that is 0. Well, that's the same as positive sine t equaling 0, and that's going to happen at points like 0, pi, 2 pi, etc. All those multiples of pi. So if we take a look at the x and the y points, because this is asking for all the points, so they want coordinates for x and coordinates for y, let's find out what the x and the y values are that correspond to these t's. So we go back up here to our two parametric equations. If t is 0, cosine of 0 is 1. If t is pi, cosine of pi is negative 1. If t is 2 pi, cosine of 2 pi is back to 1 again, etc. If I plug in 0 for this t into y, 2 sine of 0 is going to stay 0. If I plug in pi, sine of pi is 0, so this will still be 0, and so on for the rest of these. So these are going to be the points 1, 0, and negative 1, 0, and these will repeat over and over again. So far that looks like it's going to be my vertical tangent lines. What we want to make sure of is that none of these points also cause dy dt to be 0 at the same time. So let's go ahead and figure out where our horizontal tangent lines are going to occur. And that's going to happen when your dy dt, your numerator, is 0. So dy dt is going to be the derivative of 2 sine 2t. So that's going to be 2 times the derivative of sine becomes cosine 2t times the derivative of 2t, which is another 2. So this is the same as 4 cosine 2t equal to 0. If I divide through by 4, 0 divided by 4 stays 0. So we're trying to figure out when this angle 2t is going to cause the cosine to become 0. And we know that cosine is going to be 0 at angles like pi over 2, 3 pi over 2, 5 pi over 2, etc., 7 pi over 2, and so forth. All those multiples of pi over 2. But that's what this 2t needs to be. So what would just t be? Well, if I divide each of these by 2, then this becomes pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, and that's all 4 pi over 4 angles in all 4 quadrants. Now some of these may repeat, some of them may not. So what we want to investigate next here is what x and y values these are going to correspond to. So if I plug in pi over 4 for t, cosine of pi over 4 is positive root 2 over 2. If I plug in 3 pi over 4, that's quadrant 2, then this would be negative root 2 over 2. In quadrant 3, cosine is still negative, so negative root 2 over 2, and 7 pi over 4 is quadrant 4, so that'll be positive root 2 over 2. Now if I look at the y values, 2 times pi over 4 is pi over 2, and sine of pi over 2 is 1, and 1 times 2 would be 2. If I plug in 3 pi over 4, when I double that, it becomes 3 pi over 2. Sine of 3 pi over 2 is negative 1, and negative 1 times 2 will be negative 2. 5 pi over 4 doubled becomes 5 pi over 2, which is the same as pi over 2. So sine of that is 1. 1 times 2 is 2. And if I plug in 7 pi over 4, that becomes 7 pi over 2, which is the same as 3 pi over 2, which is negative 1. And 2 times that will be negative 2. So these are actually all 4 different points, because you've got x being positive and y positive, x negative, 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 positive, positive, negative. So they're all 4 different points. And none of these overlap with the points that we got over here. So we're going to have vertical tangent lines at 1, 0 and negative 1, 0. And we're going to have horizontal tangent lines at root 2 over 2, 2, negative root 2 over 2, negative 2, negative root 2 over 2, positive 2, and root 2 over 2, negative 2. And it's a good idea to just kind of do a rough sketch of this on your calculator. Put your calculator in parametric mode and graph this. If you graph it over t values from 0 to 2 pi, maybe using a t-scale of about 0.1, and a window for x from, say, negative 5 to 5, and y could go from negative 5 to 5, you're going to get a graph that looks kind of like this. So this is for t values from 0 to 2 pi. I think I use a scale usually around 0.1 for my t's. And then the x's here are ranging from negative 5 to 5, and y's from negative 5 to 5. So that'll give you a good window. And you get a graph like this, and you can see that at 1 and negative 1, which would be here and here, we're going to get those vertical tangent lines. And then we're going to get 4 horizontal ones here, 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 and here. So these points make sense. Now we have another theorem. It says that if a smooth curve C is given by x equals f of t and y equals g of t, such that the curve C does not intersect itself on the interval a to b, except possibly at the endpoints, then the length of the arc of C over the interval is given by this integral from a to b of the square root of f prime of t squared plus g prime of t quantity squared, and there should be a dt on this as well. Note that when you're applying this arc length formula, be sure that your curve is only being traced out once on this interval of integration. Okay, so this is basically the arc length formula when you are using parametric curves. Okay, so what we remember from a previous chapter when we talked about calculating arc length is that arc length was in the past the integral from some point x sub 0 to x sub 1 square root of 1 plus dy dx quantity squared dx. So it was the square root of 1 plus your derivative squared dx. So what we're going to do to this to kind of prove this formula is we're just going to do a little bit of manipulation on this. So I am going to change out this dy dx with our new formula that we have. Dy dx is dy dt over dx dt. And we want to square all of that. So now what we're going to do is rewrite this. I'm going to take this square root here and rewrite it as dy dt quantity squared. Let me make this a little bit bigger here. Over dx dt quantity squared. And I'm going to rewrite this dx. Notice what I'm going to do here. I'm basically dividing by a dt and multiplying by a dt. So those essentially cancel each other out. So I just multiplied by a fancy version of 1. And what I'm going to do then is I'm going to take the square root of the bottom and get a common denominator here as well. So this is going to become, with a common denominator, dx over dt quantity squared. This 1 is equivalent to dx dt squared over dx dt squared. And then once I have that common denominator, I can consolidate these two fractions together just like this. And when I take the square root of that bottom, that denominator is actually just going to become a single dx dt, since the square root of dx dt squared, the square and the square root cancel each other out. And by the way that I manipulated my dx on the outside here, that makes these two cancel out. And I can rewrite this as dx dt, otherwise known, since remember our function f of t was the same as x, dx dt could also be called f prime of t. And our function g of t was what y was equal to, so y prime could also be called g prime of t quantity squared. And since these cancel out, that leaves me with my dt. So this is how we sort of derive that arc length formula. So let's try it out. Find the length of the parametric curve described by x equals t squared, y equals 4t cubed minus 1 on the interval 1 to 2. So let's start by taking a look at the picture of this just for a moment so we can get a feel for what it's going to look like. So if I pull up the calculator, in my x1 I'm just typing in t squared, in my y1 I'm typing in 4t cubed minus 1. For my window, I'm just going to let my t's range from -5 to 5 with a t step of 0.1, and I'm going to let my x's range from -10 to 10, and I'm going to let my y's range from -10 to 10. So if we graph this, you see this shape here. It starts down, looking at the orientation, it starts down and goes up to this little sort of cusp, and then it arcs up from there. So let's sort of trace along here for a moment so you can see where t equals to 1 and t equals to 2, since we want to look at this on the interval from 1 to 2. So if I hit trace, and I'm just going to type in 1, and it'll jump to exactly where the point is when t is 1. So it's right there at 1, 3. And remember, our orientation was that it went down and then up. So now if I type in 2 for t, that's actually off the graph up here because y is 31, so it's way up high. So let's replicate this graph on our notes and we'll kind of see what region we're talking about. So our graph is looking something kind of like this. It comes up, touches, and then it bounces back. And t equals to 1 was about here, and then t equals to 2 was way up here. So we're talking about this arc length right here. So we're not retracing our steps at all, which is what we wanted to verify. So our arc length is going to be the integral from 1 to 2 of the square root of dx dt quantity squared plus dy dt quantity squared dt. So let's figure out what those derivatives are going to be. Dx dt is just 2t, so this will be 2t quantity squared, and dy dt is going to be 12t squared quantity squared dt. So if I simplify that and FOIL that out, that's going to give me 4t squared plus 144 t to the fourth dt. Now there is a GCF there, 4 and t squared, 4 and t squared go into both of these. So I'm going to go ahead and factor out a 4t squared, which will leave me with a 1 plus 36t squared. And the 4t squared is a nice perfect square. So that's actually going to simplify when I take the square root of it into just a 2t. But the square root will still be around the 1 plus 36t squared dt. Now remember that arc length integrals tend to be tough ones to integrate. You can't always do them. But this one is actually doable, because if we think about our square root as our outer function, our f prime, and this stuff in here as our g, the derivative of this wants to be 36 times 2t. Well, I already have the 2t, I'm just missing the 36 as well. So these pieces here form my g prime. I put in the 36, so I need a counterbalance by a 1 over 36. So this is going to be 1 over 36 out front. And when you have pattern recognition like this, the only piece that you integrate is this outer function. And the integral of a 1/2 power becomes a 3/2 power times 2/3. And what's inside stays inside, and then we're ready to use our bounds. So this is going to become 1 over 54. 2/3 times 1/36 is 1/54, and then we have 1 plus 36t squared to the 3/2, and I'm plugging in 1 and 2. So let me leave my 1 over 54 out front. When I plug in 2, 2 squared is 4. 4 times 36 is 144 plus 1 makes this 145 raised to that 3/2. When I plug in 1, I'm just going to get 1 plus 36, which is 37 to the 3/2. And I want to subtract my upper minus my lower bounds. And then this is just a job for your calculator. This is going to be approximately 28.166. Okay? Now, what's going to change if we want to find the length of the parametric curve described by that same set of parametric equations, but this time we're looking at the interval -1 to 1. So this would be the integral from -1 to 1 of that square root of our dx dt squared plus our dy dt squared dt, and it's the exact same curve, so all this inside stuff is actually going to be exactly the same, and in fact the antiderivative of all of this would be the same as well. So we're going to get the same result that we got right here, because all of this part matches. The only thing that's different between this problem number 6 and the one we're doing is we have different bounds. So I'm still going to get that 1 over 54 and that parentheses 1 plus 36t squared raised to the 3/2, but this time I want to look at it from -1 to 1. Now notice something that happens here. When I plug in my 1, I'm going to get 36 times 1, which is 36, plus 1, which is 37, so I'll get 37 to the 3/2. Then I want to subtract from that -1 plugged in, and -1 squared becomes positive, so I get 36 times 1 plus 1, which is again 37 to the 3/2. So these would cancel each other out, giving me 0. Does that make sense for our problem? No, because if you think about our graph, remember what it looked like. It came down and then it comes up again. And if you trace on that curve, you could go back to the curve, but you remember from earlier that our t equals to 1 was about here, and our t equals to -1, if you trace on it, is exactly down here. They're symmetric across this little cusp point right here. So we're getting a positive and a negative value canceling each other out. But if we use a little bit of the symmetry of this graph and realize that this arc length here should not be 0 because that's definitely got a distance to it. This answer of 0 can't be correct. So how can we fix this? Well, instead of going from -1 to 1, since we have some nice symmetry here, this point right here is when t is 0, because that's going to give you an x value of 0 and a y value of -1. So this point right here is t equals to 0, and that's 0, -1. So let's use our symmetry and take the arc length from, say, 0 to 1 and double that, and that will also give us this arc length going down here as well. So using some symmetry, we're going to change this to be 2 times this 1 over 54, 1 plus 36t squared to the 3/2. But instead of using the bounds -1 to 1, I'm going to use half of that length and go from 0 to 1. So in fact, we'll get 2 over 54, which is 1/27. And now when I plug in my 1, I'm going to get 37 to the 3/2. And when I plug in my 0, this will go to 0, and I'll just get 1 to the 3/2. And when you punch that into your calculator, that's going to be approximately 8.2986. So just be cautious if you're getting answers that don't seem legitimate. It could be that you're having some issues with direction here. So what you can do is use some symmetry to help ensure that you're using good bounds that will give you a value that makes sense for the problem. Another theorem: to calculate the area of a region bounded by a parametric curve, x equals f of t, y equals g of t, where g of t is greater than or equal to 0, in which y is a continuous function of x on the interval a to b, where a is f of t sub 1 and b is f of t sub 2, so the x values that this ranges between, and both g of t and f prime of t are continuous on the interval t1 to t2. This area is given by the integral from a to b of y dx, or the form that we're actually going to use is the integral from t1 to t2 of g of t times the absolute value of f prime of t dt. So this is kind of a complicated formula, but it's a way of finding an area underneath a parametric curve given in parametric form. We know how to find the area under a form in rectangular. We know how to find the area under a curve given in rectangular form, just y equals f of x. You just take the integral of f of x dx. So this gives us a formula for calculating the area when you're using parametric form. So it's a little bit more complicated, and it tends to be kind of tricky to use sometimes. So we're not going to do a whole lot of these, but I wanted to show you a couple. So here what we want to do is to find the area of one arch of x equals t minus sine t and y equals 1 minus cosine t. And this is actually that cycloid that we first looked at the beginning of our notes. And it looks like this, those little arches. And if you remember, these little cusps that happened were at our multiples of 2 pi. So this is going to be 0, this would be 2 pi, this would be 4 pi, this would be -2 pi. So we want the area under just one of these arches. So I'm going to look at the area between 0 and 2 pi. So what we can do here is set up our integral. It's going to be the integral from 0 to 2 pi of our g of t. Now g of t is the y function. So in this case that would be this 1 minus cosine t. So for g of t, we're using 1 minus cosine t. And then we need the absolute value of f prime of t. So we want the absolute value of the derivative of this x, since the f of t function is your x. So what's the derivative of x here? Well, it's going to be 1 minus cosine t dt. Now what makes these tricky is those absolute values. So what you'll notice here is, since we're looking at the interval 0 to 2 pi, cosine, the smallest value that it would ever take on between 0 and 2 pi would be -1, and 1 minus -1 is 2. Cosine of 0 is 1, 1 minus 1 is 0, and it's not ever going to get any smaller than potentially 0. So this value, or this expression right here, 1 minus cosine t, is actually always greater than or equal to 0 on this interval 0 to 2 pi. So since it's always positive on the interval that we're looking at, we can drop the absolute values, which makes them disappear, which makes this integral much easier for us to solve. So this is going to become 1 minus cosine t times 1 minus cosine t dt. And that then could be written as 1 minus cosine t quantity squared. Now if we FOIL that out, we're going to get a 1. In the middle, we'll get a minus 2 cosine t, and on the end, we'll get a plus cosine squared t dt. Now to integrate this, I'm going to integrate each one. So the integral of just a 1 dt, I'm going to pull out my minus 2 and integrate from 0 to 2 pi just the cosine t dt. And then for this last piece, the cosine squared t, remember that when you want to integrate an even power of cosine or sine, you actually have to use those half angle identities. So I'm going to replace cosine squared of t with a 1/2 1 plus cosine 2t dt. So now let's integrate these pieces. The integral of 1 just goes to t. The integral of cosine is just sine of t. And over here, I'm going to get 1/2 times the integral of 1, which again goes to t. And then for this piece here, be careful, you want to integrate cosine of 2t dt. That has an angle of 2t. So to properly integrate that, you need to have the derivative of the 2t present in the integral. So we would need a 2 inside, so we'd have to counterbalance by a 1/2. So this is going to need a counterbalancing factor of a 1/2, and the integral of cosine is sine, and that 2t stays put. So if I expand this out, I'm going to get t minus 2 sine t plus a 1/2 t plus a 1/4 sine of 2t, and a t plus a 1/2 t is a 3/2 t. So just combining some like terms, this is what I have so far. And now I'm ready to use my bounds from 0 to 2 pi. So if I plug in 2 pi, 3/2 times a 2 pi, the 2's cancel, just giving me 3 pi. Sine of 2 pi is 0. Sine of 2 times 2 pi is 0. So both of those go to 0. And then when I plug in 0, this is 0, and sine of 0 is going to be 0. So everything over here is 0. So we end up with 3 pi. So that's the area under one of these arches right here. Okay, to finish off, let's do one last example here, an extra example using this area formula that we just talked about. This time we want to find the area bounded by the parametric curves x equals square root of 4 minus t, y equals to square root of t, x equals to 0, and the x-axis. So the graph of this looks like this. Here's your parametric curve. X equals to 0 is just the y-axis, and then we have the x-axis down here. So we want the area under this graph. Okay? Now you can see from the bounds here that this is hitting at 2, and that's actually going to happen when t is 0. When I plug in t equals to 0, I get square root of 4, which is 2 for the x, and square root of 0 is 0 for the y. This point up here at a height of 3 happens when t is 4. Sorry, that's a 2, not a 3. So we plug in t equals to 4. 4 minus 4 is 0. So x will be 0, and square root of 4 is 2. So this is at a height of 2 for the y. So what I want to do for my integral, my area integral, remember that our formula is going to be time 1 to time 2 of your g of t, which is really your y function, times the absolute value of the derivative of f, which is really your x function, dt. So in this problem, our bounds for t, we're going from 0 to 4. Our orientation is to go this way. So we want to go from 0 to 4. Our g function, which is our y, is this one. So it's this square root of t. And our f function is this one right here. So if f of t, or our x, is 4 minus t to the 1/2, then f prime of t, when I bring down the 1/2, subtract 1 from the power, it becomes a negative 1/2. And don't forget to multiply by the derivative of what's inside, which will be a negative 1. So there'll be a minus in front of that 1/2. So that's what's going to go in my absolute values. So this is going to be the absolute value of negative 1/2, 4 minus t to the negative 1/2 absolute value dt. So a couple of things to notice here again are our bounds are going to help us with this absolute value. If t is 0, this is 4. If t is 4, this is 0. And anything in between 0 or 4 is going to make this be positive. So this expression inside of the parentheses is always positive on the interval 0 to 4. So we can drop the absolute values around it, and the absolute value will actually take away this negative as well. So the 1/2 I'm going to pull out, the negative will disappear because of the absolute values, and I get to drop the absolute value because this 4 minus t to the negative 1/2 will always be positive on the interval that we're looking at. So this becomes 1/2 times the integral from 0 to 4 of root t. And if I move this down to the bottom, let me actually rewrite this as square root of t over the square root of 4 minus t dt. And now what we want to do is try to integrate this. So my instinct here would be to do a u substitution. That denominator is kind of complicated looking. So what I might do is let u be that square root of 4 minus t, which means u squared is 4 minus t, which means 2u du equals negative dt. So dt is going to be negative 2u du. Now, what would square root of t become? Well, based on this statement right here, if I solve this for t, add t to the other side and subtract u squared, t is 4 minus u squared. So this is going to become the square root of t, or the square root of 4 minus u squared. The bottom becomes our u, and the dt becomes negative 2u du. Now we have this 1/2 out front. Let's also go ahead and change our bounds. So these bounds 0 and 4, these are t bounds. So let's figure out if t is 0, what is that going to tell me about u? If I plug in 0 for this t right here, I'm just going to get 4 minus 0, which is 4. Square root of 4 is 2. So if t is 0, that means u is 2. And that's the lower bound. Now let's look at the upper bound of 4. If I plug in 4 in for t, 4 minus 4 is 0. Square root of 0 stays 0. So this is u equals to 0. So the upper bound is actually a 0. It's okay that those are backwards. I'm going to show you how to deal with that. The 1/2 and the 2 cancel. The u's cancel. And the negative out front will actually help me with my backwards bounds, because we have a property of integrals that says you can switch the bounds around so that they go in the proper order, but that takes the opposite sign. So by flipping the order around, we cancel out the negative that we had out front. And then as a shortcut, let's figure out what this is going to equal. And you could do a trig substitution on this. That definitely would work here. But as a shortcut, remember that square root of 4 minus u squared, that's really just the equation of a circle centered at the origin with a radius of 2. And when we look at that circle from 0 to 2, we're looking at this piece of the circle from 0 to 2. So this is just a quarter circle right here. So just using a little bit of geometry, graphing this curve over the interval from 0 to 2, and noticing that that shape, that geometric shape, is actually just a quarter circle. And what's the area of a quarter circle? Well, it's 1/4 pi r squared, and our r here, our radius, is 2. So this is 1/4 pi times 2 squared. 2 squared is 4. 1/4 of that is going to cancel out. So this is just pi. So this area up here is pi. All right, that concludes our video lecture on parametric equations and calculus. Good luck.